All right, in this video we're going to be talking about language, our divided brain, right-left differences, and then the brain and consciousness. So, not going to be a very long video, so let's get to it. Language. Language depends on a chain of events in several brain regions. So when we read aloud the words, first of all, they register in our visual area. They're relayed to the angular gyrus, which transforms the word into auditory code, which then, third, receives and is understood in nearby Wernicke's area, and then sent to Broca's area, which fifth controls the motor cortex as it creates the pronounced word. So depending on which link in this chain is damaged, a different form of aphasia occurs. So aphasia is simply the impairment of language. And this can either be damage to Broca's area, which is going to impair your speaking, or to Wernicke's area, which is going to impair your understanding. For example, damage to the angular gyrus leaves the person able to speak and understand, but unable to read. Damage to Wernicke's area, again, it disrupts understanding. Damage to Broca's area disrupts speaking. What we experience as a continuous experience is the visible tip of subdivided information processing icebergs, which most of which is outside of our awareness. And remember, that's a lot like that video that we were talking about. If everything that we did, including processing and speaking language, required conscious processing, then it would take forever, and it would be mentally exhausting. So more generally, language processing illustrates how the whole mind subsystems are localized in particular brain regions, yet the brain acts as a unified whole. So this is a good graphic that shows you what is happening in your brain as you're having a conversation with your friends. Research indicates that some neural tissue can reorganize in response to damage. So when one brain area is damaged, others may in time take over some of its function. So for example, if you lose a finger, the sensory cortex that received its input will begin to receive input from the adjacent fingers, which will become more sensitive. And our brains are most plastic when we are young children. And when I say plastic, I mean plasticity is the brain's ability to change, especially during childhood, by reorganizing after damage or building new pathways based on experience. And this picture right here is a young girl who's actually missing half of her brain. This 6-year-old girl had an entire hemisphere of her brain removed to eliminate seizures. And the brain compensated by putting other areas to work. And that's actually called a hemispherectomy. Constraint-induced therapy aims to rewire brains by restraining a fully functioning limb and forcing use of the bad hand or the uncooperative leg. So gradually the therapy reprograms the brain, improves the dexterity of a brain-damaged child or even an adult stroke victim. So, for example, one stroke victim was a surgeon in his 50s, and he was put to work cleaning tables with his good arm and his hand restrained. And slowly the bad arm recovered its skills, and as the damaged brain functions migrated to other regions, he gradually learned to write again and even to play tennis. New evidence reveals that human adults can also generate new brain cells, and this is called neurogenesis. Monkey brains illustrate neurogenesis by forming thousands of new neurons each day. Our divided brain. A split brain is one in which the corpus callosum, which you've learned about, the wide band of axon fibers that connects the two brain hemispheres, has actually been severed surgically. Experiments on split brain patients have refined our knowledge of each of the hemisphere's special functions, and this is called hemispheric specialization or lateralization. In the lab, investigators ask a split brain patient to look at a designated spot, then send information to either the left or right hemisphere by flashing it to the right or left visual field. And we're going to watch a video at the end of this on this guy named Joe, and he is a split brain patient. So the two main researchers that came up with this were living in LA in the 1960s, Philip Vogel and Joseph Bogan. And they speculated that major epileptic seizures were caused by an amplification of abnormal brain activity between the two hemispheres. So, I mean, it's kind of like a biological tennis game. And so what they said was, well, let's sever the corpus callosum and see if that will stop it. So the seizures were all but eliminated once they did this. And moreover, the patients with these split brains were surprisingly normal. Their personality and intellect hardly was affected, and then waking from surgery, one even joked that he had a splitting headache. And then these people, Myers and Gazzaniga, their studies of people with split brains provide a key understanding to the two hemispheres' complementary functions. And there's a good graphic right here that we can talk about. The peculiar nature of our visual wiring enabled the researchers to send the information to a patient's left or right hemisphere. And as the person stared at a spot, they flashed a stimulus to its right or to its left. And they could do this to you too, but in your intact brain, the hemisphere receiving the information would instantly pass the news to its partner across the valley, but not so in patients who had undergone split brain surgery. So think of it like phone cables that were responsible for transmitting messages from one hemisphere to another. They had been severed. So this enabled the researchers to quiz each hemisphere separately. So in an early experiment, Gazzaniga asked the patients to stare at a dot as he flashed heart on a visual field. So let's see. Look at the dot. Two words were separated by a dot, and they were momentarily projected. So really, the whole word is heart, but they see he and art. So he appeared on the left visual field, which transmits to the right hemisphere, and art in the right field, which transmits to the left hemisphere. And when he asked what they had seen, the patient said they had seen art. But when asked to point to the word with their left hand, which was controlled by the right hemisphere, even the patients were startled when they pointed to he. So given an opportunity to express itself, each hemisphere reported what it had seen. The right hemisphere intuitively knew what it could not verbally report. So when a picture of a spoon was flashed to their right hemisphere, the patients could not say what they had viewed, but when asked to identify what they had viewed, they readily selected the spoon. A few people who have had split brain surgery have been for a time bothered by the unruly independence of their left hand, which might unbutton a shirt while the right hand buttoned it, or put grocery store items back on the shelf after the right hand had put them in the cart. And it's like each hemisphere had its own personality that was doing two different things. And with the split brain, both hemispheres can comprehend and follow an instruction to copy simultaneously different figures with the left and the right hands. And this guy right here is Joe. And he underwent a split corpus callosum sever surgery because of his epileptic seizures. And this is a short little video. I want you to watch it.
I know the left hemisphere and right hemisphere now are working independent of each other, but you don't notice it. Now, you just kind of adapt to it. You don't have any feeling different than it did before.
7 years ago, Joe had brain surgery to allay the effects of severe epilepsy. His surgeon cut the nerve fibers connecting his left hemisphere with his right. While the operation was a complete success, Joe's unusual case offers an extraordinary insight into the machinery of mind. This fiber system, the corpus callosum, is located midway between the two hemispheres. When it was surgically severed in Joe's brain, the transmission of information between the two hemispheres was halted. Michael Gazzaniga.
What we can do is play tricks by putting information into his disconnected, mute, non-talking right hemisphere and watch it produce behaviors. And out of that, we can really see that there is, in fact, a reason to believe that there's all kinds of complex processes going on outside of his conscious awareness of his left half brain. Joe, I'm going to show you some things. I just want you to tell me what you see. And here we go. You ready? Look right at the dot.
Okay.
Right. Okay, you ready? Look right at the dot.
Grapes.
Good. When Joe focuses on a point, look right at the dot. Everything to the right of the point goes to his left brain, the dominant hemisphere for language and speech.
Look right at the dot.
So we can see here that when we flash a word or a picture, Joe is easily able to name it.
Here we go.
See it.
Close your eyes and let your left hand do a little work here. Okay, what do you got there?
Pen.
Okay, very good. Now, when a word or a picture falls to the left of a fixation point, that information goes to his disconnected right half brain. And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain. Good job.
Okay.
What'd you see?
Wheel on one side. I don't know what it's on the other.
So even though he can't name it, his left hand is able to draw out the picture of the stimulus of the picture or word that we presented to his right half brain. What did you see?
It's a hammer.
So just close your eyes and draw with your left hand. Just let it go. That's nice. What's that?
Saw.
Yeah. What'd you see?
Hammer.
What'd you draw that for?
I don't know.
What we have with Joe is just a dramatic example of a neurologic case that really allows you this window into the non-conscious and how powerful non-conscious processes are at influencing our conscious self, our personal self. What Joe and patients like him, and there are many of them, teaches us is that the mind is made up of a constellation of independent, semi-independent agents, and that these agents, these processes can carry on a vast number of activities outside of our conscious awareness. Even though that goes on, there's some final stage or some final system, which I happen to think is in the left hemisphere, that pulls all of this information together into a theory. It has to generate a theory to explain all of these independent elements. And so, and that theory becomes our particular theory of ourself and of the world.
So that's a really neat video showing you Joe. So let's talk about some differences in the intact brain. Quizzing each hemisphere separately, researchers have confirmed that for most people, the left hemisphere is more verbal and the right hemisphere excels in visual perception and the recognition of emotion. Studies of people with intact brains have confirmed that the right and the left hemispheres each make unique contributions. So, for example, the left hemisphere makes quick lateral or literal interpretations of language, and the right hemisphere excels in making inferences. So take this, a good example of this is this picture, for example. Look at the center of one face and then the other. Does one appear happier? Most people say that the right face seems happier, and some researchers think this is because the right hemisphere, which is skilled in emotion processing, receives information from the left half of each face when looking at its center. So, some more information about these different hemispheres and what they do. Studies reveal that the left hemisphere is more active when a person deliberates over decisions. When the rational left brain is active, people are more often, they'll discount disagreeable information. The right hemisphere understands simple requests, easily perceives objects, and is more engaged when quick, intuitive responses are needed. The right side of the brain also surpasses the left at copying drawings and recognizing faces. The right side of the brain is better with emotions and perceiving emotions, and right hemisphere damage therefore more greatly disrupts emotion processing and social conduct. Well, let's go back to this real quick. About 10% of us are left-handed, and almost all right-handers process speech primarily in the left hemisphere. Left-handers are more diverse. 7 in 10 process speech in the left hemisphere, and the rest either process speech in the right hemisphere or use both hemispheres. Left-handers are more numerous among those with reading disabilities, allergies, and migraine headaches. Left-handedness is also more common among musicians, mathematicians, professional baseball and cricket players, architects, and artists. The advantages and disadvantages of being a lefty seem roughly equal. So, I love this picture. Consciousness is our awareness of ourselves and our environment. Cognitive neuroscience is the interdisciplinary study of how brain activity is linked with our mental processes. And it's helping us to understand how specific brain states relate to the conscious experience. Most cognitive neuroscientists are exploring and mapping the conscious functions of the cortex. Based on our cortical activity patterns, they're beginning to read our minds. For example, they can tell which of 10 similar objects we are viewing. Cognitive neuroscientists and others studying the brain activity underlying consciousness have discovered a two-track human mind, each with its own neural processing. Perception, memory, thinking, language, and attitudes all operate on two levels, a conscious deliberate high road and an unconscious automatic low road. And researchers call this dual processing. Conscious information processing enables us to exert voluntary control and to communicate our mental states to others. And beneath the surface, faster unconscious processing occurs simultaneously on many parallel tracks. And clearly, much of our everyday thinking, feeling, and acting occurs outside of our conscious awareness. And that's kind of the video that we watched the other day on The Amazing Brain. And if you want to go back and watch that, it's on the blog. It's called This Is How Your Brain Works. And that talks about dual processing, except they call it fast thinking and slow thinking. And they talked about priming and the conscious left brain and the intuitive right brain. So, and again, you've got your two-track mind right here, visual perception and visual action. Visual perception is simply, let's see. Well, we don't need to talk about that actually. So, again, dual processing, two-track mind. If you have any questions, raise your hand, and we have some psych sims that we're going to do. Thanks, guys.